Hello, everyone. So yes, my name is Minko Gechev. I'm a senior engineer in the Angular team at Google. I joined Google a little over a year ago. Before that, I co-founded a company, Rime.com, which recently got acquired by Coursera. So thanks to this deal, now Coursera has an office here in Bulgaria. That's something I'm pretty excited about. Originally here on this presentation, I was going to talk about the future of front-end frameworks. Since I'm working on Angular, I have some idea how eventually the frameworks can evolve in the future. But I was on a digital forum in San Francisco about a month ago. I was talking to different customers who are using Angular or other front-end technologies. And one of them told me that their production build takes 30 days. That was a lot of time. Imagine you're doing your quarterly planning. You're in the conference room, like discussing your OKRs, and one of them is building the application. Like this shouldn't happen. Imagine you're waiting 29 days in order to remember that you have forgotten a semicolon and your build fails. That's not ideal. In Google, we are building daily, like billions of lines of code. For example, we have hundreds of millions of lines of TypeScript. And our code production build, when we change the TypeScript compiler, takes about 2 hours. That's still with consumption of a lot of assets, a lot of resources, since we're executing the build in parallel on hundreds of thousands of CPUs. Today, I'm going to discuss a couple of the practices that we are using in order to speed up our build that much. They're applicable not only for TypeScript, they're in fact applicable for everything because we're using the exact same build system to build our TypeScript code as well as Java, C++, Kotlin, and so on and so forth. So the agenda for today. First, we're going to discuss why do we actually need a build process, why we need a build system in JavaScript. Building web apps was not supposed to be that complex. Like a couple of years ago, maybe 10 years ago, I was just copying and pasting jQuery from the jQuery website. After that, we're going to discuss how our infrastructure in Google 3 looks like. Google 3 is our monorepo. And we're going to try to pretend that we can build this thing with the tools which are widely used externally, such as Webpack. After that, we're going to talk about how we are actually building applications in Google. And finally, we're going to discuss the tools that allow you to do that and some open source alternatives that you can use today. First, let us talk about web apps in 1991. That's the first website ever, like it's still online. It's pretty simple, right? We have just an HTML document with a bunch of hyperlinks, and it is still fascinating. We can navigate across different hosts this way by just clicking on a single of these hyperlinks. That's pretty powerful. We have this distributed system. But life was much simpler. We used HTTP 0.9 and HTML. And that was it. No CSS, no JavaScript, like everything was much, much simpler. But over time, the requirements for building web apps, they started evolving. We want to build more and more complicated web apps. And this is how, on the 5th of March, 1995, the browser vendors decided to start working on JavaScript. So that was the language which was going to power the web. Currently, JavaScript is the most popular programming language. About 9 days later, JavaScript was born. And we're still trying to fix it. We are constantly talking to different people, like as part of Angular, we're also working with TC39, the JavaScript Standardization Committee. And there are a lot of sketchy things out there. Anyway, currently, when we're building a web app, we're considering several different things. First, network protocols, because we have HTTP, we have WebSockets. We are using different programming languages. We don't necessarily have to use only JavaScript. We can use, as part of web, we actually have HTML5 and CSS3, which are Turing complete, in fact. So every program that is computable by the Turing machine is computable by HTML and CSS, which is pretty impressive. And on top of that, we have different browser APIs. During last week, I was on Chrome Dev Summit. There, Google Chrome announced that they're working on a native file system API, and you can already try it in Chrome Canary by enabling the experimental flag. So the Chrome project Fugu aims to provide native APIs for all the developers who are building web apps. In general, any web application any application that you can build for native devices, any native app, you can build it for mobile as well, for web as well. So currently building a web application in 2019 is a little bit more complicated than just taking a bunch of scripts and putting them into an HTML page. Because we ask the business, what do you want? Do you want the power of a desktop application or the convenience of a single web app? And of course, everyone wants both, right? And in the process, to build a single page app now, we need to pick a programming language that we're going to use, so a compiler, whether we're going to use TypeScript, PureScript, Sass, and so on and so forth. We need to pick a build pipeline, minification, bundling, static analysis, application framework like dependency management, module system, CI, assertion library, and so much more. In fact, we have CLIs, like the Angular CLI, for instance, which is trying to simplify our life by taking some of these decisions for us and bootstrapping, scaffolding our application automatically. There are a couple of challenges once you have to use these tools in scale. There are people with different backgrounds. For example, there are folks who prefer to use rollup compared to Webpack because, well, rollup is much more minimalistic compared to Webpack, which is much more powerful, but a little bit tricky to configure sometimes. We have projects with different size. So our infrastructure needs to scale well. And there are also different people with different development experience. We want people to be portable across projects, in our organization at least. Now, let us look at an example. This is a very, very, very simplified example of the Google Cloud Console, like extremely simplified example. Here we have Google Cloud, which has some front end, some user interface that we can interact with, and a backend, a bunch of backend services that are doing a lot of things. The front end depends on Angular, as well as Angular Material. Both Angular and Angular Material depend on TypeScript. And here is what the complicated part is. Only the UI is over 3 million lines of code. So that's a lot of code. And still, this is only a small fraction of all the TypeScript code in Google, which is hundreds of millions of lines of code. In fact, currently, TypeScript is the official language for building user interface. So if you have to build UI in Google, you must use TypeScript. You cannot start the project with JavaScript. If we had to build this project by using the state-of-the-art tooling right now, we will have used NPM Install first to install all the dependencies for this project, which is 3 million lines of code. And after that, we're going to run webpack dot in order to build the project with webpack config in the current directory. Let us forget about NPM Install for a second and think and see whether we can make webpack scale that well. Obviously, the first time that we run webpack in the current directory for all these 3 million lines of code, we're going to get out of memory, right? It's expected. What we can do is decompose our application into several sub-applications. For example, we can have the UI for compute in one sub-application, the marketplace is in another, and the security portion in the third one. Later, excuse me, we can combine these and produce the final application bundles. So this way, we can even build them in parallel. We can execute each one of these application builds in parallel so that we can utilize our CPU completely. All right, so that's in our very simplified example, where our build graph is very simple as well. We have just one main application and a bunch of passenger apps, which are completely independent from each other. But in real life, the build graph is going to be slightly more complicated. And maintaining this build graph ourselves is probably not the best idea. We need to first build this graph ourselves. We need to maintain it depending on the application imports and make sure that all of these sub-applications are orthogonal. After that, once we decide to build, we need to apply a topological sort so that we can find the sub-application without any dependencies and build it first. We need to distribute the independent tasks across different CPUs or cores on our CPU. We need to synchronize the build tasks, and after that, collect the build artifacts. This is quite verbose. And again, this is something which could be easily automated. If we want to write these scripts ourselves and still use Webpack, that's fine, but we need to be able to move them across different projects so that our developers can move across projects very easily as well. So this custom logic is not ideal as well. The only easy part is collecting the build artifacts, which is just taking the production assets and pushing them to a CDN. Different problems here are a lot of boilerplate logic, which is pretty much the same across projects. We don't have any incremental builds. Webpack 5 is working on incrementality, but we still don't have it out there. We have cross-language dependencies sometimes. Imagine you have a very complicated Java backend with a communication schema for the front end, something like Swagger or Protos or whatever you prefer. You have also the backend and the front ends, and you need to establish somehow a dependency across them, so that when you update the communication schema, you're going to rerun your integration tests across the front end and the back end as well. These cross-language dependencies cannot be expressed with the modern JavaScript toolchain. In order to have good development experience, we also need fast round-trip time. This is the time until you save a file in your editor once you have modified it, and the browser reflects the changes. You also need a fast initial code build. But let us first look at the initial fast round-trip time. It turns out that Webpack does not scale that well. Once we started building larger projects with Webpack, we noticed that the time to build grows like pretty much exponentially after this point that I have visualized on the chart. As well, for the initial code build, they're not ideal as well. So Webpack produces a lot of side effects. Even with this caching, we would frequently have to discard the cache. And parallelizing across different cores is not something that Webpack supports out of the box. We need to use external plugins. So this is somehow supported, but still not ideal. Now, in the second part of the presentation, let us see how we are doing these things in Google. First, let's start with NPM Install. NPM Install is like NPM is probably the sketchiest tool that we are interacting on a daily basis. Someone recently was crypto coin stealing from a utility module that had 2 million downloads. Like imagine you have, or you can, with the same success, you can even mine Bitcoins on everyone who is using this module, right? So also if you run sudo npm install, the post-install script can just pretty much destroy your file system. So it's risky. Every time when I'm running npm install, I'm praying that someone is not going to steal my proprietary information on my laptop, for instance. That's why we are not using npm. It has a bunch of security vulnerabilities. Also, if we want to vendor all the packages in a private registry, we need to maintain it, so that's a lot of work. And having many different versions of the same library is not ideal either. Why is that? Imagine if we had many different versions of Angular. Well, having many different versions of Angular, this means that the projects which haven't migrated to the latest version of Angular yet, they cannot take advantage of the latest security fixes and performance improvements that we did. That's why we are using a monorepo. This means that all our entire source code, which is like literally billions of lines of code, is in the same repository. We don't have any security vulnerabilities. If we want to use a third-party package from the external world, it needs to go through a very, very strict security review by different specialists. And after that, once we approve it, and we can migrate all of its transitive dependencies together with itself in our monorepo file. A huge benefit of the monorepo is that we can reuse infrastructure very easily. We need to have only a single continuous integration system, right? We have a single monorepo. We can reuse code very easily as well. All we need to do is just import a file from a different directory inside of this monorepo. Enforcing a single version policy is really easy as well. So the library authors, they're responsible for fixing all the applications that their libraries break. For example, in Angular, once we push a new version, we first need to go there and make sure that we haven't broken any of the internal Angular applications within Google. This means that every time when we sync Angular from GitHub to our internal monorepo, we're running all the tests of the affected packages, and if any of them breaks, well, we are rolling back in order to see what was actually wrong and fix it. So we feel the pain across incompatible forward releases, and we're trying to fix this. If you're interested in learning more about our Mon repo, I'll definitely recommend you to look at this paper, Why Google Stores Billions of Lines of Code in a Single Repository. This paper is going to give you more details about our network file system, about our version control system, and much more. Now, let us talk about how we're actually building, because that's the topic of the presentation, right? So far, we have been only talking about how we are managing the source code. We're using a tool called Beso. There are a couple of great things about Beso. It is a universal build tool, so you can build JavaScript the same way that you build Java. It is a functional build. I like to call it functional build because it has some properties that purely functional languages have, and this allows us to implement very efficient caching as well as parallelism. And it hasn't changed for the past over 10 years. Definitely we cannot say that for the external JavaScript ecosystem, right? We have a new build tool every other week. Now, let us talk about how Beso works. So I had the privilege to work very closely with the Beso team because with Angular, we want to make sure that our enterprise customers scale well. And it is really a fascinating work. So here is our Google Cloud model again. If we translate this to our Mon repo, this is going to look something like that. This is, again, very, very simplified. It doesn't look exactly this way, but it is good enough to give you an impression how things work internally. We have Google 3, which is the name of the Mon repo. Somewhere inside of this Google 3 directory, we have a directory called Angular. That's where we keep Angular. Notice that inside of the Angular directory, we have a build file. This build file contains the build instructions for the current directory, for all the files in the current directory. We have Angular core. So building Angular is probably going to involve building Angular core as well. And the instructions for building Angular core are in the build file in the core directory. It is very easy now to import Angular in the Google's front end, Google Cloud's front end, directly from the Angular directory in the Mon repo, right? Of course, we're not going to use like .. / and so on and so forth, because there could be many levels of nesting. We have aliases, but that's how pretty much everything works. We keep the TypeScript compiler there as well. So it is very easy to migrate to the latest version of the TypeScript compiler once Microsoft releases it. We have an entire team dedicated on migrating the TypeScript compiler every time when Microsoft releases a new version. So they pretty much fix all the compile time errors for all the applications in Google. So one package defines a compilation unit. And Basil can compile multiple compilation units in parallel. So this is pretty efficient. We can look at one build file, for instance. Here we have ng module. This provides instructions on how to build a given Angular module. You can see that this ng module has a bunch of sources. These are the inputs to this ng module rule. We have an entry point, which is an input for the rollup bundle rule as well. They also have dependencies and names. You can see that the rollup bundle depends on the source rule, which is the ng module rule that knows how to build the given ng module. From there, if we want to build the bundle, we're first going to build the ng module, and right after that, we're going to pass the assets to the ng module rule, to the rollup rule, excuse me. So that's a very simple build file. ng module, you can think of it as a function, because this looks like pretty much like a Python function call syntax with named argument, named parameters. You can think of it as a function which configures the build system somehow. From there on, we can compile the files just by invoking Basil build :src. These targets, which are the function calls. For example, here we had two targets. We have the src target and the bundle target, which we have created by using the ng module rule and the rollup bundle. These targets, they cannot produce any side effects. In fact, you need to define what are the outputs that they're going to produce, and Beso is going to validate this for you. If they produce other inputs, other outputs, or they don't produce any of the ones that you have declared ahead of time, Beso is going to throw an error. So this is pretty much inspired from lambda calculus in the end, right? It's just a bunch of pure functions which communicate together somehow, like they're just which we compose together in order to build our entire application. I like thinking of Beso and the pure functions as Beso targets. The immutable data structures are pretty much the build artifacts, and these pure functions, they can be very easily memoized and run in parallel. So we have caching and parallelization out of the box. Now, if we look at our higher level execution algorithm, first, discovering the build graph. You notice that we're declaring the build graph statically inside of our build files. So by running Beso query, we can query our entire build and get a diagram similar to the one here. This is actually generated with Beso automatically. I just run Beso query, and after that I piped the outputs to an image generator. This isn't a convenient way to debug your build, right? It is just a bunch of pure compositions. That's all of it. Now, the topological sort, the distribution of the independent tasks, and synchronizing the builds and collecting the build artifacts, all of this you can achieve just by running Beso build :app. And this is true for JavaScript, for TypeScript. It is also true for Java as well. Like, you can use this across many different technologies, because that's the technology that we're using for building everything. Now, here is what is going to happen. This is from the system monitor of one of my colleagues. He ran Beso for like building Angular probably. On his machine, he has quite a few cores, as you can see, like 12. Beso is utilizing all of them. So that's actually good. The current build systems for JavaScript, they're going to build everything into a single thread, onto a single core. And that's not optimal. When you have 12 cores, why should you use only a single one? But if you're building a large application, you may not have enough cores. So in this case, you can execute your build in the cloud. There are build farms widely available that you can just set up in your local network. And by using gRPC, Beso is going to directly talk to them so it can schedule different build tasks. There are different strategies in this case. You can run both you can start a build task in your local machine as well as in the cloud, and later both can race with each other and you can take the fastest one. This is the dynamic strategy of execution, for instance. Caching is very efficient as well. You have, by default, your disk cache, so everything you build is already cached. But if you're working in a team, as most of us are, you can have a remote cache, which is shared among all of your teammates, as well as your CI. So once your CI builds the project, you don't really need to rebuild the project at all. You can just take all the cached assets from the CI's cache. So remote caching is probably the most powerful feature of Basil. And you can implement it on-prem pretty easily just by using Nginx. Now incrementality. The cool thing about Basil is that the time to rebuild is proportional to the change that you have made, not to the size of the project. Luckily, Webpack 5 is going to introduce this as well. I hope this trend keeps going in the future. Once you change a single source file, you don't have to recompile your project. You can recompile only the changed source files and all the affected packages from there. So here is how Beso affects the changes. In TypeScript context, Beso is going to compile the changed file. It is going to check whether its type declarations has changed, whether its TDS file, its DTS file has changed, and from there, if it has changed, it is going to propagate the execution to the affected modules. Otherwise, it is going to just recompile this file and output the JavaScript associated with it, and that's it. Of course, in Google, once we update the TypeScript compiler, which is just another Basil package, we need to recompile everything, right? Because we are invalidating this build graph. But this happens in very rare occasions. Compared to make, Beso recomputes, verifies whether a file has changed based on its hash. So it is going to compute the hash for your packages, and if they haven't changed, it is not going to recompile them. In general, it maintains a Merkle tree which allows you to propagate the changes to the top. There are a bunch of open source solutions. For example, Beso is out. It was released about 3 weeks ago. It's a 1.0 version, and it has been out since 2015. So now it is officially announced as stable. A lot of companies started experimenting with it. From what I know, Dropbox are already using it in production, as well as Lyft, Asana, and a bunch of other companies. You can have self-hosted remote caching, and there are a lot of open source build farms. Uber maintains one of them, and it is widely available. It is pretty much on GitHub. So here are a bunch of resources that I would encourage you to look at. First, the paper. I'm starting from the bottom. Why Google stores all these billions of lines of code in a single repo. I noticed this trend. It's happening very, very frequently nowadays. A lot of people started migrating their multi-repository projects to a single monorepo in order to encourage code reuse and shared infrastructure. Build System a la carte is a fantastic paper, which is going to give you a great overview of how Basil compares to Make, even to Excel, because Excel, the software, like the spreadsheet management, it is a bunch of incremental computation algorithms which aim to recompute the minimum number of cells in your spreadsheet. So it solves very much the same problem as Basil. They're pretty close. You can also see how to use Angular with Beso and the official Basil documentation. Beso also loves Angular. We have been working together with the Beso team for over 2 years now. We're building Angular with Beso, and we're trying to verify that it works well for our enterprise customers as well. So if you're using Beso and Angular, let me know. I would love to chat. That was it. Thank you very much for your attention.
Guys, it is now time to just address questions to Minko. So raise your hand if you have such. So a Google engineer and no questions. That doesn't go together.
You can also find me in the hallway after that and chat. So it's fine.
Thank you for the nice lecture. We know that we're talking about Google with their huge code base. Do you know of any other company in the world that has such problems with their builds?
Yeah, I'm talking to a lot of customers, a lot of big banks. They are having a lot of trouble with this as well. Also, Dropbox recently migrated to Beso. Lyft migrated their build from Gradle to Beso. I saw a tweet about that like yesterday, I think. A lot of companies are going in this path, specifically moving their code to a monorepo and from there figuring out their build system depending on their needs. Beso is a great tool for some organizations, but of course not for everyone. If you have a relatively small project, I would encourage you to keep using the default Angular CLI setup, for instance.
Hi, thank you for the presentation. I have one question, maybe a stupid one, but where your test code is stored? Again in the same monorepo or?
Yeah, same monorepo.
Same. Oh,
yeah,
okay.
And we have just a couple of instructions in the build files about how to run the tests. Basically, Beso is going to delegate the execution to whatever testing framework is used internally, like underneath.
Okay, thank you.
Hi, thank you for the presentation. And my question is regarding the versioning into the libraries which are coming from the monorepo. And you said that if once change a library code, then he should go and fix all the other things that he has breaked. And here the question is, if the one that is creating the library wants to change the version of the library, how this affects the clients of this library?
Yeah. So the library of Angular internally is 0.0.0. Like, it doesn't have real version. It's just a placeholder, like the version itself. We just take the files and push them into the Google 3 monorepo. And from there, our internal CI is rebuilding all the projects that depend on Angular. If any of the tests fail, we need to investigate why they fail. Is that problem in Angular or it's a test fake? And we just start debugging and to figure out what's wrong. If it is regression in Angular, we automatically fix it. If it is a breaking change, we roll back because it's a breaking change, and if it is not a major release of the framework, we cannot afford this. If it is a major release, we go and fix the user application. For example, if we break messages.android.com, we're going to go and fix it and submit a change list, like a pull request, one you can call it, to the Android team.
Okay, so into the monorepo, you always have one and the same version of all artifacts there. So there is no any artifact into monorepo that is referencing different version of the library that is in the same monorepo.
Yeah. It's the same version of,
Okay,
exactly.
Thank you.
Sure.
Last chance for questions, guys. If not, give your big applauses to Minko.